be x over 5. This one happens to say every 3 hours. And so instead, when you go to set this up, here's your doubles. So you start like this. We're doubling. This is my rate. I don't know what we put in here. Oh, here they are. Sorry. We initially put in 2,500 units. We're doubling. This would be every hour. But we didn't do it every hour. We did it every 3. That's where the divide by 3 comes from. And I was telling them yesterday, it's a good way to start this way. Start with a little table. At the 0, this is what you began with. At the 3 hours, I should double this. Every 3 hours, I should double it again. So when you put this in your calculator, you can go to your table and you can actually see that those values are there. Oh, okay, thank you. Have a Merry Christmas.
Merry Christmas.
Okay, so
How do you know when you use this formula and when you use like PERT?
well, we don't use PERT at all on these. PERT is only when it involves compounding interest, which is money. So that's the only time we use this, the N, and the PERT. The rest of the time, and they actually fit your AB to the X format. It's just we have a little compounding in there. So I always start y equals AB to the X. So in this case, your initial value, that's your A. Your rate, we said yesterday. This is a good thing to write down. If you double, then B is 2. If you half, then B is 1/2. If you triple, what should B equal to? 3. If sometimes you have a population increase by 1% or a decrease by 1%, then you have to do 1 plus or minus your rate, and that would be your B. And we'll look at those in a minute. Okay? You okay? Okay. You have your homework?
Yeah.
Okay. All right. So now, what we said we had to do was to do this graphically. Very good. You can keep your pass by that label on the side. This is your Y1. Well, this one just had nothing to graph right here until we got down to here. You're going to put in your 6 hours into here. You can actually graph this and take it right off your table in your 6 hours. We could calculate your 6 hours pretty fast that way, just by running every 3 hours. Or you can just put this in your Y1. Now, when you go to your graph, and we said yesterday, you just kind of have to be careful because you're going to have to change your window. Again, you're in quadrant 1. So we're okay in quadrant 1. We know our mins are zeros. We can't have negative times. Our graph actually comes from quadrant 2 because all your exponential increases come this way. All your exponential decreases go this way. So the complete graph shows this part, but the application says only quadrant 1. So when we graph this guy, which disappeared, see if today I do any better at my graphing. When we graph this, here's my rate, I'm doubling, okay, and I'm going to go every cycle x over 3, and I just put it up in my exponent. X divided by 3. Now, that's my initial value. I'm going to get a lot of bacteria here if it keeps doubling every 3 hours. So in my window, I don't want to set my X max to 100. Maybe I just want to set it to 10 right now. And my Y max is what I'm looking at. If I started at 2,500 and I could see after 6 hours I'm 10,000, maybe make this 30,000. See where we go with this. See what it is you're graphing. So we can take a look at your exponential growth of your bacteria. And the second part said, when will it be 100,000? So therefore, now I want to set this guy to 100,000. Maybe make it 120,000, just in case you can't see the top of it. And you're going to set your Y2 to your 100,000. Okay? And we're going to see where they intersect. Algebraically, we can't pull an exponent down unless we use a log statement. So when we come back from vacation, we're going to do the logs. And we will actually revisit all these applications and solve them algebraically. Right now we can only solve them graphically. Now this tells me right here, well, whoops, I'm not meeting, so what do I have to change? My x. Good. So I'll make my x max 50. And see if that helps me. It also, when you do that, it also makes it a little steeper. So you could see the increase a little sharper. And then just do an intersect on it. Hit the intersect 3 times. And there's your answer. Don't use a trace, because a trace is not going to get to that exact spot where it intersects. Round this, and this is where you intersect, but I want x equals 15.966 hours. That's what I expect as an answer. Don't show me the point of intersection. Don't give that as your answer, because that doesn't tell me which one is your answer. So make sure you give me your answer on this. So for you guys that were in here, is it making sense? Nick, Azure, making sense?
Yeah.
Kinda. We pretty much follow a basic formula. This one, again, we did this in class yesterday, so just to review for them, this one's like a little bit different. It still starts with AB to the x, but I have a percent decrease here. So how do I write my decrease in terms of my rate? 1 minus. Because what a decrease does is, it says, well, you can take 2% every time you do this, leave me 98% of it left. So whatever the value happens to be of your rate. So we take away your rate, and it retains this part of your unit, of your population in this case. So again, we know that a decreasing exponent curve goes this way. This is your complete graph. This right here is your situational graph. Situational because we can only be in quadrant 1. We can't have negative time. So we kind of stop right here and we just look at your quadrant 1. And we want to see when does it decrease to 50,000, which is a lot for it to decrease. From 123,000 at a little over 2% every year, it's going to take you a little longer to get there. I think we looked at one yesterday that decreased like maybe 3,000. So of course that wasn't a big one. Can everybody do this and set their windows? Jen, you weren't here either. Is this making sense? Okay. We always work off of this equation. I find the easiest way to start is to start there. So your initial value goes in here. That's the first one. Your rate is the B. Well, I'm not doubling, I'm not halving, I'm not tripling. I'm decreasing by a certain rate. That's my 1 minus this guy. And again, x is my exponent for time. So algebraically, we're going to come back after the break and visit these with logs. But right now, we're going to just do them graphically. Okay. Stop me if you have any questions. Half-life. You guys do half-lives in chemistry. According to Dr. I, we do half-lives in chemistry. So we say, okay, start basic. What's my initial value? Okay, so I've got my initial. What's my rate?
1.5.
Just 1/2, right? Just 1/2. I'm not doubling. I'm halving every time. And my time would be in days. X would be in days. Am I half-lifing every day?
No.
Every 14 days. So divide by 14. So if you look at your graph, let's think about this logically. At the 0, I have 6.58 grams of this substance. At the half-life, which is how many days? 14. How many grams should I have? Like 3.79? 3.79 grams, right? And when do I half-life again? And how many days? 28. I take half of this again. 1.8. 0.95 or something like that. So when you look in your table, after you write your equation, if that's not there, then something went wrong. It's a good indication that you did it right. Now, you want to get down to less than 1. You want to get down to less than 1 gram. So we're just going to set it equal to 1 right now. And look how small your numbers are. So you might want to just start with a Zoom 6 and just redo your minimums right now. So I've got 6.58. I'm taking a half life. Oops. And I'm going to raise 2. I jinxed myself yesterday when I said this was working so well. X divided by 14.
Wait, so when it says write the amount A of substance remaining as a function of time, it's just writing that equation?
Yes, this is what you're giving me. Y equals 6.58, 1/2. And don't forget, your exponent only goes to this 1/2. You can't multiply 6 times the 1/2. It only belongs to the 1/2. So now when we want to hook this up with 1, you might just want to start with the Zoom 6. And then see it decreasing, where it came from quadrant 2. Okay, so now I'm going to just change my windows here. And I noticed that must have been pretty big, so I'll just go to 20 right now. And keep it here and see if this works. If it's not working at 20, you have 2 choices. Look in your table to see where it's going, or just keep doubling this until you hit it. You really can't ruin your window. If it works out that you kind of got messed up, go back to a Zoom 6. And now I'll be able to take my intersect and find out how many days I have.
Wait, y2 is what?
Is 1, because you want to know when there'll be less than 1 gram. So at the end, when we intersect, we find this to be your point of intersection. So X has to be greater than this many days to be less than 1. This has to be a little bit more than that, doesn't it? Because when it starts, it's always decreasing. So when is it less than 1? It's 1 at this, well, we had to round, but it's 1 at this time. So we say our answer is as soon as it's less than that, it's greater than that. Even if I pick this up a little notch. So the concept is still the same. You're graphing, your y2 is the amount that you want to reach. Where they intersect is your exponent, because your exponent is your variable right now. Are we kind of seeing this? Yeah? Okay. Alright, number 4. Again, let's start this. We're watching our rabbits double. So start like this. Y equals AB to the X. What's my initial count for rabbits? 20. What's my rate? Double, which is 2. And X would tell me every month. Okay? Are they doing it every 5 months? Every month. So my X days every month. So now, this is where I start. This is my function. So they asked after 1 year. Now the problem with 1 year is we measured this in months.
So it's 12 months.
So it's 12 months. You have to put a 12 in here. Then 5 years, you have to put a 60 in here. And you could have graphed this if you wanted to. It's probably just easier just to plug them both in. The last part, sorry, we got to do one more part. Determine when there are 10,000, that's when you're going to graph. I'll move this down in a second. Are we all okay with this? Now, your calculator writes this. E19 is the same as 10 times 10 to the 19. It's a scientific notation number. It obviously can't be this small because you're doing this a really long time. So watch that E part. That's your scientific, and leave it in scientific notation. This one will be a very, very large number because you have to move your decimal place to the right 19 places. I would prefer it in the scientific notation too. And the last part of that, you just had to graph. You had to graph when it was going to be 10,000. Mine were in thousands. And do an intercept. And we were pretty close on this. This was after 1 year. So it had to be a little bit after 1 year. Or, wait a minute. Oh, we're all looking for 10,000. This one was after 1 year, and we had already reached like 81,000. So if we're only looking for 10, it's got to be within that 1 year. So just let your ass go from 0 to 12 months. You'll hit it in that time. And we found out it was 8.966 months. Remember your 3 decimal places. Are you guys good with this? A lot of this just involves changing your window all the time, because the formula really is not changing. Just memorize y equals ab to the x, and that works with all of them. The only time you're compounding, though, is with your interest problems. You're not compounding on these guys. We don't want you to compound 12 the months. Only the interest problems compound. Okay? This is very similar to your other population, except now this is a happy town because it's increasing. So when I start like this, I start with my population. I'm increasing, I'm not doubling, I'm not tripling, I'm just increasing 1 plus my rate. Remember to put them in decimal form. There's your equation. And your complete graph says, your complete graph, since you're increasing, came like this. That's why these guys never start at the 0, because you're starting with something here. This is my complete, this is my situation. Right? Believe it or not, Algebra 1 kids are doing, they're not doing the graph like this, but they're doing some of these exponential graphs.
For the window, the y to, the x window, going the x with the y max.
This is your y max. This is your y max, and right now you probably don't know your x max, so you have 2 ways to do it. You could look in your table to see where your y is that number, what is the x, and set it, or you can just set it at 10. If it doesn't meet, double it, or if it looks like it's really far, then go to 40. You can just play with your x max. But these are not going to be like a really large number. It's not going to be like hundreds of years. And most of the time, they're pretty quick. But this is your y max here. When you want to reach something, that's a good y max. And I would go just a little bit further sometimes, because it writes up at the top. If you're intersecting at the top, you may not see the words. So I'd go to like 1,200,000. Just so that you have enough space up top to do this. And when you do this on a test, guys, this is what I expect from your graph. They're either going to look like this, increasing, or they're going to look like this, decreasing. That's what I'm expecting from show me your graph. No one has any questions. Everybody can do this. Alright, again, this one is basically the same. Here's your increase. It's increasing. It started at a certain population. It increased. But the only thing was you just had to find x. So I gave you the year that we started the population, the year we ended it. So subtract those and you'll find your x. I think the first one was 1890 to here. So 1890 to 1915, we had to do that one, and then 1915 to 1940, from 1940 from here. So you had a 25 years and a 50 years. You did not have to graph that, because If you can fill in all the right-hand side, that's what goes in your calculator. You don't need your y equals. Put it right in your calculator. And when you're talking about population, be careful where you round. Andrew?
So what, like sometimes you put X over something?
Well, X over is when it says, and that's a very good point. When they say up here, see the word each year up here? That's my X. If they say every 5 years, then I'm X over 5.
Okay.
Okay, so now, and then your population, be careful of your population. You want to round. You want to round to a whole number. Generally, we should round down because you never reached this number yet. But since it's within that year, it's probably going to happen. So just make sure you round to your people. Because population has to be whole numbers. Years, you have to give me your partial, your decimals. Bacteria units, your decimals. But I don't know how exactly they measure the bacteria units. Okay. Here's another half-life. This was a nice one. Now here's a good example of it, Azure. I'm doing days, so it would be, the X is in days. But it said to me, take a half-life every 65 days. So I have to do X divided by 65. Very similar to the one before. You wanted to see when it reached 1 gram. And every 65 days, that's your X value. So if I'm decreasing and I want to get down to 1, 65 days is going to put me down to 2.5. 120 days is going to put me down, well, half 1.75. And then under 1, I'll be in 120. So you got to figure, at least give your X up to 120. You're half-lifing.
But if it was like the half-life of a certain reaction solid is 1 day, they just
Put X. They'll always give us like what they wanted it, days, months, years, and that's what our X would represent. The X would be days, the X would be months, the X would be days, years. But sometimes they will say in 3 months, in 14 days, in 65 days, then that's over that number. And think about it logically. If you made a chart, this is why I want you to think this out. If I start my chart with 3.5 grams and I take a half-life, 1.75 is my half, right? And when did I get 1.75? How many days did it take me to get to 1.75? 65 days. See, it didn't go every day. And then another 65 days, I'm half of this, so this is less than 1. Whatever that happens to be, less than 1. So my 1 has to fall in here somewhere. So I like to do this first, because I think it gives you a perspective on this. Where are my numbers going to look like? Plus that also helps you do your window. I can kind of get a feel for where my window is going with this. Okay, and again I gave you another half-life. You have a half-life of a certain substance in, look how fast this is, in seconds. So you initially started with 2 grams. You want to know how much is left after 1 minute. But your graph is in seconds. So don't forget to convert that 1 minute to 60 seconds. You actually didn't even need to graph it, because if you can fill out the whole right-hand side, your graphing is every 1.5 seconds. That's your cycle. So 1 minute would be 60 seconds. Just plug that in here and stick it in your calculator. You can figure that out. Oh, you had to find your substance this time. So how much you started with. So when you're here, remember that this belongs to this guy. So divide everything by this. Just divide everything by that and you'll find how much you started with. You started with a big substance. Look how fast you're decreasing. Every 1.5 seconds, you're halving. got to have started with the big substance, right? And you're doing that for a minute. So it's going to have started somehow a little bit larger. And leave it in scientific notation. You could graph that if you like and do it that way, absolutely. Or you could actually just divide this out if you wanted to. Okay, start like this. What is your initial grams that you're starting with?
6.
6. What's your rate?
1/2.
1/2. And we're doing this in seconds. Is it every second?
10.
10. So I divide by 10. Everybody get this formula? Now, you have a couple of choices here. I'm asking you how many are present after 10 seconds. So X would be 10 seconds. How many are present after 20 seconds? So X would be 20 seconds. After 55 seconds, what do I have to do? Put 55 over 10. I'm just substituting them in. So Y equals 6 times 1/2, 10 over 10. Basically, 1/2 to the 1 is
3.
well, 1/2 times 6 is 3. Okay, I'm just substituting them in.
1.5.
You got 1.5, and then I'm going to do a 55. And what'd you get for this?
0.133.
Thank you. Now, I could do it that way, or I could throw this whole thing into my Y1. All I have to do to throw it in my Y1 is just put it in Y1, and I don't even care what my graph looks like. And then just go to my table and look up each one. Just show me your substitution. So when I do this, I'm just going to put in my 6 times 1/2 raised to the X divided by 10. Oops, wrong. X divided by 10. Watch, guys. I don't care what my graph looks like. I don't even care if I couldn't see it. I just need to go to my table. So all I want to look up in my table is when X was 10. There's my 10. When X was 20. There's my 20. And when it was 55, I'll just jump it to 55. And there's my 55. Okay? Let your graph do that part for you. Are we good with that?
Yeah.
Okay, let's try another one. Everybody get this one set up. Okay, she wants to know what would the population be in 10 years. Where does that 10 go? Oh, with the X. It just goes in place of the X. In place of the X. There's no divide by. So in 10 years, all I'm going to do is substitute this in. 10 years. This is my time. My time in years. So in 10 years, how much will my population have increased? This 1 plus rolls in your new population all the time. Now, you can absolutely put this in your Y equals. Again, if you put it in your Y equals, right at this point right now, I don't really care what my graph looks like at this point. So I can just go to my table. And I'm just going to put 1 plus 0, 5. Oh, is it 1, 5? Oh, 5. Yeah, because I just added it together. I just added it together. And we're going to erase this 0. Now, I don't care what my graph looks like. I just need to know where is the 10. So I look for my 10. Let's go back to my table, started at 10, and tell me what my population is. There's my population. Let me scroll over it and make sure. Here's my population. 20,571 people.
You could just plug that in the calculator, right?
Absolutely. But I knew this next part was coming. So I figured you can absolutely plug it in, or you can put it in your y equals. Now to do the next part, I want the second one to say 25,000. That's weird. 25,000. So now I might want to change my window. I'll go to 40 years. I need this to be like 30,000. Well, you need it to go to 25,000, right? When will your population be 25,000? So I want to intersect it with my 25,000. So second calc, do an intersect, hit it 3 times. And there's my answer. I'm looking for the years. So 13.958 years. I'll have reached 25,000. My little town is growing. And graphically, you're going to show me this. You're increasing, you're crossing. 13 point, I forgot what I said, 958, thank you. And we say years.
Would it be your window?
Yes?
Yeah, would you make
Well, an easy way to make your window is this. Because I have to reach 25,000, that's my Y max. Just go a little higher on your Y max, because sometimes when you intersect, you can't see it at the top. It writes like over the stuff up there. And I don't know what my X is going to be. I could set it at 20. I know it can't be too big because I'm not really increasing that much. So maybe, I had mine preset at 40, which was fine. If they don't intersect, redo your X. Are you guys good with this? Okay. Tomorrow, test. Well, let me say one other thing. Make sure on the test that you remember how to do these guys. Okay? Homework 1 and 2. I start with my basic graph.
Oh, what's the transformation?
Yes, where does this transformation bring me?
To the left.
To the left 3. Where does this transformation bring me?
Down.
Down 5. So you're going to keep track of your domain, your range, and your asymptote. Okay?